Can I start?
Yes.
Yes.
Yeah, good morning to everyone. I'm going to present this article in account of chemical research on the topic of this photodynamic therapy, heavy atom free photosensitizer from molecular design to application in photodynamic therapy of a cancer. As we know that this photodynamic therapy (PDT) is a clinically approved therapeutic modality that has shown a great potential for the treatment of cancer owing to its excellent spatio-temporal selectivity and inherently non-invasive nature. However, PDT has not reached its full potential, partly due to this. How I can minimize this part? Yeah, fine. However, PDT has not reached its full potential, partly due to the lack of ideal photosensitizer. A common molecular design strategy for effective photosensitizer is to incorporate heavy atom into photosensitizer structure, causing concern about elevated dark toxicity, short triplet state lifetime, poor photostability, and the potential high cost of heavy metals. To address this drawback, a significant advance has been devoted to developing advanced smart photosensitizers without the use of heavy atoms to better fit in clinical requirement of PDT. Yeah, the mechanism of this how this heavy atom free photosensitizer works. First, the injection of this photosensitizer in our body, then followed by this PS accumulation in our body, then activated by a light, then selective destruction of tumor takes place. The mechanism of for, the mechanism of this process is explained by the Jablonski diagram. First, the molecule is excited by photoactivations, goes from ground state to singlet excited state, and the molecule in singlet excited state comes in the ground state, that is called fluorescence. And in this singlet excited state, molecules go in a spin forbidden triplet transition state that is that is having more lifetime as compared to singlet excited state. And in this triplet excited state, molecules come into ground state, that is called phosphorescence. And another and in this there is another way, that is these two types of mechanism happen, that is type 1 and type 2, that is called hydrogen or electron transfer. And one is this type 2, that is called energy transfer. In the energy transfer, uh, the free radical and reactive oxygen species important when the oxygen levels are low. And in, this is in the electron transfer. However, in the energy transfer, the main source of the main source is a singlet oxygen, and the dominant cytotoxic species in PDT. As we have seen that most of the photosensitizers are derived from the tetrapyrrole, like porphyrin, chlorine, bacteriochlorine, and phthalocyanine. Tetrapyrrole structures make up the largest group of photosensitizer that have been employed for the anti-cancer application. Tetrapyrrole backbone occurs naturally in several important biomolecules such as heme, chlorophyll, bacteriochlorophyll, and in fact, this tetrapyrrole have been termed as this pigment of a life. author manuscript is phthalocyanine also have a large band in this 670 nanometer region. Broadly speaking, this tetrapyrrole photosensite tend to produce predominantly type 2 singlet oxygen compared with the type 1 reactive oxygen species, and these are more often produced by photosensite with other structure. The main approaches used to design this heavy atom free photosensitizer, trying to reduce this energy gap between this singlet excited state and the triplet excited state, that is this delta EST, so that there is an efficient singlet oxygen generation happen. By these are the conventional carbonyl compound. By replacing this carbonyl to this thionation induce intersystem crossing, as we can see that the gap between singlet excited state and triplet excited state, that is ISC, is reduced by substitution with thiocarbonyl compound, and then this efficient singlet oxygen generation can happen. And there are the various consequences of this heavy atom-free photosensitizers. The first, this spin orbit charge transfer intersystem crossing. The heavy atom effect is a typical method used to enhance the ISC, that is intersystem crossing of organic compound, but this method suffers from some drawback such as toxicity and a high cost of synthesis if precious metals are involved. Moreover, the triplet state lifetime of photosensitizers can be shortened by the heavy atom effect because it enhances both singlet to triplet as well as triplet to singlet ISC processes. Triplet photosensitizers with a long triplet state lifetimes are desired because the long-lived triplet state is more efficient at sensitizing singlet oxygen in a hypoxic environment of a tumor tissue. Second is reducing the singlet triplet energy gap, that is delta EST. As we know that ISC is formally spin forbidden by the selection rule. However, ISC can be partially allowed when there is a suitably spin orbit coupling or a remarkably small energy gap between the singlet and the triplet state, that is delta EST, and this can be described by the following rate constant that is defined by this equation. And third, as we discussed earlier, that thionation of a carbonyl group in a conventional fluorophore. And this naphthalamide derivatives carbonyl compound, and this gap between homolumo, that is it is 4.15. By substitution at this NN dimethyl, this energy gap is reduced. This is 3.46 electron volt. However, by replacing this carbonyl compound with the sulfur, as previously this energy gap is 4.15 electron volt, it reduced up to 3 electron volt. And by again putting this NN dimethyl in this thionation compound, this energy gap between HOMO-LUMO is 2.73 electron volt. And we can see that this, when the energy gap between this singlet excited state and the triplet, that is spin forbidden. However, in the case of this manganese sulfur compound, the gap is less, so there's an efficient population occur. And fourth is the twisted pi conjugation system induced intersystem crossing. These are halicine molecule. It has been known that halicine, which is an aromatic hydrocarbon with a twisted pi conjugation framework, has intersystem capability, and ISC efficiency is correlated with the torsion extent of the molecular structure. In a non-planar aromatic molecules, a spin orbit coupling between two pi star state increase compared to that in coplanar molecule, as the removal of And in this molecule, the removal of mirror plane symmetry allows non-vanishing matrix element associated with each molecular or orbital angular momentum, that is Lx, Ly, and out of plane Lz. Thus, by this way, this ISC can be enhanced. These are the heavy atom-free photosensitizers based on the sulfur substituted biocompatible carbonyl fluorophore. These are the proposed mechanism that this triple-state generation and the PDT effect in cancer cell of a morpholin substituted thiolnaphthalamide. And these are the chemical structure and the PDT effect of this NIS methylene toward the cancer cell of under 2 photon excitation. And in this slide, this heavy atom-free photosensitizer based on the naphthalamide platform. There are three naphthalamide derivatives. On the basis of this spin orbit coupling charge transfer, ISC strategy naphthalamide derived Trojan base was prepared and studied for IC properties. The molecular structure of naphthalamide Trojan base is rigid, which is beneficial for spin orbit coupling. ISC efficient intersystem crossing, that is up to 41%, and the long triplet lifetime, that is 46 microsecond, were observed in deaerated DCM. Trojan base had a high toxicity, that is 5 uh, nanomolar under an irradiation dose of 1.2 joule per centimeter square, which is more potent in PDT. And in conclusion and outlook, there are several disadvantages of these photosensitizers still need to be addressed for the clinical translation. For example, most of the current heavy photosensitizers suffer from low water solubilities and a serious ECQ, that is aggregation cause quenching effect in aqueous media due to the rigid structure along with the poor tumor selectivity, which reduces their clinical outcome. By devising water soluble and non-aggregating photosensitizer, attaching targeting group to photosensitizer, or introducing nano delivery system, the above and by this way the above drawback can be solved to improve tumor imaging and therapeutic efficacy. Thank you.
Nice presentation, Abhishek.
Yeah, thank you.
You go to that slide that where you have shown that heavy atom free photosensitizer, few examples you are showing, right? How exactly in this case intersystem crossing is happening without heavy atom?
In which case, this case,
Yes.
and in this case, what he said that uh, we are going to destroy the cloplanarity. By that way, this they are getting more spin orbit coupling.
Okay.
Like here, he explained that in non-planar aromatic molecule, this spin orbit coupling between these two pi to pi star state increase as compared to this coplanar molecule.
Okay, but in case of this heavy atom, the orbitals are involved directly, right, for intersystem crossing.
In the case of heavy atom, this they are decreasing this EST, delta
Yes.
EST between singlet and triplet.
So that is happening in case of other system. Let other example, it is happening by the planarity distortion. That gap is reduced.
That is another way to enhance ISC.
Oh. Okay, but in another example where thalidomide, naphthalimide, and other
Ah,
cases are there.
naphthalamide derivatives.
So
Yeah.
their planarity difference is not there, right? Like
In this molecule they are not talking about this coplanar planarity disturb.
so then in this case, how this gap is reducing? Like in this case also, this energy gap will be reduced only, right? Then
हाँ
then only you will be able to get good this photosensitization. So that is simply because of more no conjugation, I think. Like some advantage.
In this molecule also they describe on the basis of this spin orbit charge transfer, but exactly I don't know that what factor affect to reduce this ISC to enhance the ISC.
You go on previous slide, one back.
This one.
Yes. So here what they are trying to show in slide 10 you go.
This
Here
one.
they are taking similar system, right? The same system, the naphthalamide system.
They are trying the same system and study how this means affecting the cancer cell.
I think here only they have shown like this system can work as a efficient ROS generation. So this system, maybe this whatever the electronics it is there,
Like
it is the same.
here they explain by replacing this oxygen into this sulfur and by substitution of this NN dimethyl. So he observed in this case by both replacing carbonyl and NN dimethyl, this energy gap is 2.73 electron, that is very much reduced. So on the basis of this concept,
That may be
they
the
try
reason. So it is
this
getting created.
morpholin derivative they attach, and this carbonyl is replacing by sulfur. So they find that this potent in cancer cell, efficient potent in cancer cell.
Yeah. It means here they have shown that wherever they have N substitution is there, that substituent is responsible for the shift
हाँ
in absorbance. Okay. Okay, good. Thank you.
Hello.
hello.
A nice presentation, Abhishek. You go to the slide number 10 or some 8, you go. So this one, like, I think Andy has told while you are discussing with her regarding this one, this is similar molecule to anthracene carboxamide, right?
Yeah, हाँ
So
this is
in her molecule, she also told like compared to this amide, the carbonyl, if you means change that with sulfur, there is some biological importance is there. Do you remember why they have used sulfur instead of oxygen?
like means she's saying that this naphthalamide derivatives are already reported.
Okay.
So these naphthalamide derivatives, when this replacing by oxygen sulfur by oxygen,
Uh,
sorry, oxygen by this sulfur, so this
uh,
enhance the intersystem crossing.
okay.
In anthracene carboxamide,
Hmm.
if we replace carbonyl with the sulfur, so that will also be like give the same type of behavior.
Yeah. Same type of behavior. So, like, if you see the trend, they have see in the subset all these four, there are two variation. One is oxygen to sulfur, and keeping the dimethylamine in the para position.
Mm-hmm.
So, with the both factor that is applying on the last molecule that has the least energy of excitation,
Ha, ha,
e.g.
ha.
So, is it because of the wavelength control? Because if you just see the
Like,
comparing with oxygen to sulfur, that also from 4.15 to 3 it has decreased.
yes,
And
yes.
that dimethylamine also that also has decreased the value. So applying the both condition
Both.
here, that is having the least energy of excitation, right?
Yeah, I think that this para substitution, it is going to like this is like electron donating. So
True,
maybe
true.
this lone pair is going to contribute or this change into this carbon sulfur bond. So
Oh, okay.
that's why the means this anion dimethyl as well as this sulfur both are contributing to reduce this energy gap.
Okay, 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 okay. And I don't know, maybe I think it's very basic question. I might have some confusion. Like this fluorescence and all we see, right? So that's ultimately electronic transition, right?
Yeah, yeah, huh.
So is it like in whatever the anthracene, carboxamide or naphthalene? What is the major excitation like this N to pi star or that kind of a transition? That's what it involves here, or something different it is involving? Or singlet to triplet, is it different or
Like
same thing?
carbonyl is there, so N to pi star is there, as well as aromatic ring are there, so pi to pi star is also there.
Okay. Yeah, that's what I had like this whatever this fluorescence is nothing but the excitation of N to pi star or that's something different or something like that I thought. Yeah, and also if you see this they are calculated energy, right? Difference in energy. So this is through computation or this have you seen the paper like through
No, no, it's
computation
like
normal?
some DFT study
Oh,
in
that's
this paper,
DFT. Uh,
DFT study. Uh,
so that we can't do. Like at least if you can take it as one of your perspective for your work also. Like it's fine. You can just have a look into it.
yeah,
Like if
yeah,
in case like I don't know energy minimization and all. Like if in case you can do it with whatever the research we can have, that you can add into your work also. That will be good addition. Like here also they are very clearly showing how the energy is changing, right?
yes, yes, yes,
So you can show something like that also on add-on studies if it can be done. You just have a eye on that kind of a study also.
yes, yes.
Okay, thank you.
Nice presentation, Abhishek.
Yeah, thank you. Yeah.
Just I have one doubt. Like in this process, like this method, ultimate goal is to get the triplet like ISc conversion.
IC converts, more like
Then that will,
a molecule should be more lifetime in a triplet state.
yes, yes. So to get that, they are having like kind of conjugate system, more conjugate system, and somehow electron donating system.
Yes, yes.
So, like if you go to like I think four or three number slide number three, I think.
Yeah.
No, come down. Other one. Like, what about this system? This slide number four.
Slide number 4. This one. For this.
Haha.
Uh,
They have did you check this, like how much triplet lifetime for these compounds?
I didn't check, but
No,
if
people
you
has done.
like if you if you see most of the like 90% photosensitizers are derived from this tetrapyrrole
Porphyrin
type
ring.
structure.
Okay.
Porphyrin ring, porphyrin chlorine bacteria. These are means out of 190 molecules of photosensitizer are derived from this porphyrin derivatives.
Exactly, by seeing the structure, the much conjugation they are getting here, they will not get by
Huh.
like carboxamide or the anthracene. I don't know about the cytotoxicity about these compounds, but yes, if they are looking for only to generate the triplet oxygen or the
Hmm.
like increase the lifetime of the triplet state.
Like if you this mechanism like in this triplet lifetime triplet excited state, there are two types of mechanism occur, like type 1 and type 2. So
Okay.
that like in type 1, this hydrogen or electron transfer that generate reactive oxygen species, and this is going to help in photodynamic therapy. Like
Hmm.
this is going to kill the cell.
Okay.
So so if the molecule are more stable or more lifetime in this triple state, so more possibilities of this reactive oxygen species as well as this singlet oxygen generation can be happen.
Yes. Only thing like that should undergo this intersystem crossing. Not
Like this
yes.
intersystem
ISC
that's
conversion.
this IC conversion should be a very efficient way.
Yes. Okay, Abhishek, that much only. Thank you.
Okay, thank you.
Good presentation, Abhishek.
Yeah, thank you. Yeah.
My some suggestion is there. You use this slide is not this standardized slide, I think. So much space is both side of your slide.
Okay.
And go previous slide.
This one.
No. Where you are writing units of this energy.
Where? Units of
Before
energy.
one. Uh,
Here.
no. Where you write in the slide, you typing. So you are not writing in superscript and periscript. You are writing direct and somewhere.
That is like you are saying
My
that about this
suggestion.
format.
No. You write kilojoule per centimeter square somewhere. But
Okay.
my suggestion, you